All right, it's 11:15. We'll get started. Any questions, comments, anything that people want to talk about before we get going with today? Yes.
For the first problem in the homework, I'm kind of confused on like maybe how we get MN. Do we find the degree of polarization from the content provided?
Yeah. So this is a good question. You're all going to want to hear this. If you don't have number one on the homework yet, don't forget your homework tonight. So the way you find MN, which is in grams per mole, right? You know how many grams you have, right?
Right.
So all you have to do is you need to find the number of moles of polymer. And the trick to this question is, what type of polymer is this in terms of what does the chain look like? It says in the problem. Linear. And so because I tell you it's a linear polymer, that means it's got 2 N groups for every chain. So when you start counting N groups, if you have 10 moles of N groups, that means you only have 5 moles of polymer. And it's a little bit harder than that because acetic anhydride splits into 2 moles of acetic acid. So you have to do some very careful accounting of what could be going on the polymer. So I suggest you have like number of moles of acetic acid attached to the polymer and number of moles of acetic acid left over, because that's what you're titrating. So you need to write out the equations and figure out where everything is going, and you can get it from that. Okay. But yeah, there's 2 N groups per molecule of polymer, which means if you have 2 moles of N groups, you have 1 mole of polymer. Or if you have 5 moles of N groups, you've got 2.5 moles of polymer. And so then you just take the grams divided by the moles, and then you get grams per mole. Okay. And you're going to get an MN of something in the thousands for that answer. I won't tell you the exact answer, but it's going to be a little bit lower than we usually think of as a polymer, but it's not going to be like 200 or anything like that.
I see. Okay.
Is that cool? Yeah. If you have a question, shoot me an email. I'm probably going to be available till like 3 o'clock today by email, but I'll try and clean up anything tonight. But make sure that one is a tricky one because there's a lot of stuff going on. Other questions? Yeah.
Have you made any more progress on the reopen?
I will get that done. Yeah, this weekend. It's on my list. Yeah, I know I owe you some of that. Other questions? Good. Okay, so we have a few more things to do, and next week is a regular week. So homework, we're going to talk about mechanical properties and all that stuff. We'll have PLAs, and so next week's just a regular week, no exam, nothing like that. All right. So we were talking about another type of thermal characterization, differential scanning calorimetry, and we talked about what differential means, what scanning means, and what calorimetry means. And so the way that this technique works is it's measuring heat flow. And measuring heat flow tells us whether the process is exothermic, gives off heat, or endothermic, requires heat. And so in order to interpret this data, this is just what the equipment looks like. You'll see, you'll see lots of plots like this. So you'll have heat flow on one axis. And in most differential scanning calorimetry plots, heat flow is positive in the up direction. But that is not always the case, depending on whose software you're using or something like that. You want to look at the direction of the heat flow, whether heat flow positive means it's going into the sample, heat flow negative means it's heat is coming out of the sample. So heat coming out of the sample, and that's exothermic. And then heat going into the sample endothermic. And from the direction of the heat flow, which is whichever way the peak is pointing, you can figure out whether it's an exothermic or endothermic process. And then in this case, you have to remember what is melting and what is crystallization, and are they exothermic or endothermic? Yes.
Yeah, for the negative, actually, no.
You cool? Okay, we'll keep going. Ask it again if it keeps bugging you. So we're measuring the heat flow as a function of temperature. And so what we're doing is we're slowly warming up this sample as a function of time. And we notice in this case, and this is where we finished last time, that as we warmed it up, heat was given off. It's a negative peak in our heat flow. That means that heat's coming out of the sample. And we know that crystallization is an exothermic process. We get the heat of fusion back, right? And so how can we be heating a sample and it crystallizes? Usually, what do you do to water to crystallize it? You cool it, right? So in most small molecules that we're used to, we have molten iron, we've got liquid water, we've got whatever liquid, we cool it to crystallize it. So how can we heat a polymer and it crystallizes? The answer is that polymers are special and cool, and so I'll tell you about it. So that's really important. And the important thing you really need to remember is that out here somewhere, there's this theoretical temperature called TM0, which is the equilibrium melting temperature. And that's the theoretical value for 100% crystalline polymer. Of course, that doesn't exist. Or an infinitely thick polymer crystal, that doesn't exist as well. And so all the crystallization and melting of polymers always happens below TM0 and above TG. And we'll talk about that over and over and over. Okay, so right away, as you can see that this measurement is conducted, you can get polymer to be crystallizing as you're increasing the temperature. Of course, the polymer can crystallize as you're cooling as well. So polymers behave like regular liquids. You can cool a semi-crystalline polymer down and it will crystallize. Where does crystallization and melting stop? So we talked about TM0, which is the highest temperature, but what is the temperature at which we can't do any more crystallization or melting? TG, that's right. Because the chains are frozen, so all crystallization and melting occur above TG. Once you go below TG, party's over. You get some little physical aging that you'll be able to study later, but physical aging is not crystallization, it's just a densification. All right, let's see. Where the heck is our TG slide? Oh, yeah. So because crystallization and melting are both first order phase transitions, they both have a peak with an area. And from this area equals delta H of melting, delta H crystallization, delta H fusion, whatever you want. So when you integrate that and normalize it by the amount of sample, you can get the delta H because it's a first order phase transition. Glass transition temperatures are what order phase transition? Second order. There's no delta H for a second order thermal phase transition. And so that's why the glass transition temperature just gives you this baseline shift, which is indicative in the difference in the constant pressure heat capacity of the glass versus the melt. So if we look back here, the glass versus the melt have different slopes in specific volume versus temperature. They've got different CTEs, right? The melt or the rubbery part of the polymer above TG has a different slope than the glass or the glassy part of the amorphous polymer below TG. And if they've got different specific volume versus temperature, they likely have different heat capacities as well. And so that gives us this baseline shift. And how we compute the TG is we usually just take the half height of this baseline shift. And so we assign that to TG. So now we're going to be looking at DSC thermograms that have these baseline shifts, one at the glass transition temperature, and we're going to have peaks pointing down and peaks pointing up, depending on if the polymer is crystallizing or melting or what's going on. And so we want to start to interpret those things. Question, yes?
Would it be possible if we decrease the temperature really fast that it gives the crystallization rate?
That is a good question. And so the question was, if you go from above TM0, so remember, above TM0, there's nothing can happen. There's no crystals, there's nothing. We're always in the melt because we're above the equilibrium melting temperature. And if you take that sample and like plunge it into liquid nitrogen and cool it as fast as you can, there's no time for those polymer chains to organize into a crystal. It takes time to grow a crystal. And so you can cool the sample below TG faster than the crystals can form. So you can quench the polymer to be amorphous. And I have that on a slide coming up. Yeah, so quenching is the act of going from a high temperature to a low temperature. And so you can prevent crystallization. Now doing that, you freeze in a lot of free volume, right? So if you quench a polymer, you can get significant physical aging. It's hard to measure the TG under those conditions. There's other things that happen when you quench, but you can definitely prevent crystallization. Good questions. Anything else? All right. Okay, so we talked about TC as the crystallization temperature. And if the heat flow is oriented in this direction, you know, there's no guarantee that I'm always going to write the arrow this way on your exams or whatnot. And so make sure you look at the orientation and decide if it's an exo or endothermic process. And since this is an exothermic process, we assign it a TC. And by the same token, that if the heat flow is positive, we know that melting is an endothermic process. And so you can think about, you have to add energy to break up that crystal, right? Crystals are low energy thermodynamic state, or the most stable thermodynamic state. And so in our conventional ideas about small molecules where you have to heat ice up in order to get water, you could remember this one. You have to add energy to break up the crystal. And so you need to absorb heat into a crystal, and that's why it's endothermic. And that's assigned a TM because you're melting the crystal. And remember, out here is some theoretical TM0. So TM can be close to TM0, but it can't be above it. All right. So what a real DSC thermogram looks like is something like this. And so there is a TG somewhere. This is labeled TCC, and that stands for cold crystallization. TC and TCC are the same thing, but one's happening under conditions where you're already made some crystals. And so, we'll count that as a detail. TC is more important for this. And then you have TM, which is our melting temperature. So what's interesting is that you can get plots like this either as you're heating or as you're cooling. So typically, if you start from, let's say here's TM0. So if I start from TM0 completely in the melt and I start cooling that polymer down, what temperature am I going to hit first? What's the first thing that's going to happen? If this polymer is semicrystalline, if it wants to crystallize, I start at high temperature in the melt and I start to cool it down. What's the first temperature I'm generally going to see? Did I have anything to melt though? Well, TC, yeah, TC or TCC. And so let me insert a slide. So if I have my temperature and I have my heat flow, I start here above TM0 and I cool this down. So I'm moving in the cooling direction first. So I take my sample, put it in the pan. I have my reference. I have everything. I heat it up. Everything is amorphous above TM0 and I start cooling it down. I'll actually get a TC first. So I'll get crystallization upon cooling. If I keep cooling the polymer down, what thermal transition am I going to hit next? If I keep cooling, TG, good answer. I really don't see a TM because you really can't melt anything when you're cooling, right? That'd be a very unusual situation. So you see some crystallization. You could actually see multiple crystallization peaks depending on your cooling rate. And so you get some TC. So this is step one. Yes?
So does it start already melted or is it a solid?
It's completely melted because we started up here above TM0. We'll get the other case in a second.
So if it started melted, then you can't melt anymore.
Can't melt anymore, right? Yeah. So the second run, step two, same polymer sample. We start from the glass. And so we go up here. What's the first temperature we're gonna hit as we start to warm this polymer up? It's not a trick question. Oh, what has to happen first before I get to any TMs? TG. Have to go through TG or else nothing can happen. So TG's first. Now I'm heating this polymer up. And so it's already crystallized, right? I'm going to have to hit a TM sometime. But what can happen is that I can get a little bit more crystallization on heating. Depending on how fast or slow I'm going, depending on what the state of the polymer is, I can get more crystallization. Then eventually I'm going to get a TM. And then I'm going to go above TM0 and it's all completely melted. Notice that TM is always higher than TC for the same population of crystals. You'll learn that in 400 level polymer classes, but TM is going to be between TC and TM0. And so we can call this TC1, we can call this TC2, and we might even see a little TM for any extra crystals that we formed on the way up. Yes?
So TM is only available when temperature.
That is correct. You can only melt crystals when the temperature is increasing because it's an endothermic process. So you need to supply some. Yeah. Yes.
So there's just going to be equal line I think for those TMs up there, or is that saying like it's going to be happening earlier?
What's going to be happening earlier?
TM, like that TX.
Oh, well, so we can assign TC1 and TC2 to different populations of crystals. So this might be TM1, where the one crystal's melted, and this might be TM2, where the second population of crystals melted. Because it turns out the size of the crystal depends on TC. You'll get into all of that in your upper division classes. But this is why TM and TC can move around between TG and TM0, because the size of the crystals really influence the crystallization and the melting. Yes?
I'm just confused, when we heat up, why is there crystallization?
Yeah, so if the polymer still wants to crystallize, so if it's still a semi-crystalline polymer, you can have some extra crystallization until you hit the maximum crystallization for that polymer. So if you have incomplete crystallization here, say you quench it a little bit more and you go below TG, it can't crystallize anymore, or those crystals are really slow to form and you didn't give it enough time. When you start to heat it up, you can get crystallization because of that. That's complicated because now you've got two different populations of crystals and they have their own thermal transitions. It gets tricky. You'll study the X-ray scattering of that, other things like that in your 400 level classes. But this is important because this shows that when you start from the amorphous polymer above TM0, you get crystallization first to form those crystals as you cool it down. Yes?
No matter if we're heating or cooling, whatever it's between PG and TM, it can crystallize.
That's right. Now, let's do one more scenario here. Let's start from here. Low temperature. First thing that's going to happen is TG. So we're going to go through TG. We're going to go from a glass to a rubbery polymer. What can happen when we're still below TM0? What temperature could we hit next? It could crystallize a little bit more. You could get a TC. And then you heat it up a little bit more, and what are you going to get? TM, great. And then you're going to get above TM0, and nothing else happens. Great. So that's all good. The one transition that you may not see is if the polymer is fully crystallized, and let's do one more. If polymer is fully crystallized during processing. So during processing means as we're making the sample, as we're doing whatever with our polymer, we've got heat flow. And we have temperature. So we heat this thing up above TG. And if it's fully crystallized, if it's 100 or not 100%, but if it's at the maximum crystallinity for that polymer, say like 70% for high density polyethylene, or 30% for PET, what's going to happen first? If we just can't form any more crystals in this polymer, what's the thermal transition that we're going to see? TM. And we have TM0 here, of course, which is theoretical temperature. So in a lot of cases, the polymer is as crystallized as it's going to be. It's sitting, in your iPhone case or sitting as a sample. You're just going to heat it up. You're going to see the TG, then you're going to see the crystals melt, and then it's an amorphous melt. So this idea that TC happens on heating is for incomplete crystallization. Like if we quenched the polymer, so if we took a semicrystalline polymer from TM0 and we quenched it to below TG, the driving force, because it's a semicrystalline polymer, is to crystallize. So as we heat it up above TG, it will crystallize, then it will melt. So this is quenched sample. Okay. So it can get complicated. I will give you scenarios that are easy to figure out, things that are completely crystallized during processing, samples that are quenched. And so your job is to figure out, based on the direction of the heat flow and what the shape of the curve looks like, is it a TG, is it a TC, is it a TM, et cetera, et cetera. And of course, TDEG is way out here, and then the polymer is not the same polymer anymore. Yes.
So in this instance, when do the crystals form then?
So the crystals, in this instance, the crystals formed during processing, which we don't see in the DSC. So say you take a plastic part that came off an injection molding line or some sample out of a bag. So the crystals formed during processing. So you didn't measure any crystallization. Yeah, you just melted the crystals. Does that make sense? Great. So there's a lot of cool stuff about thermal analysis, and you can combine this with X-ray scattering and other things like that, which will be in your future classes. But this gives you the basics in terms of what a TG looks like, what a TM looks like, what a TC looks like, and some of the features of each. Questions or comments? All right. So some oddities of TM, and these are just bullet points that you can remember. Melting and crystallization temperatures depend on the thermal history of the polymer. How was it heated? How was it cooled? It turns out if that polymer was stretched, that can affect the crystallization as well. So there's all sorts of processing things that have to do with crystallization that you'll learn about in the future. Melting behavior depends on heating and cooling rates, and let's say melting and crystallization. So it's all rate dependent. TM or TC can occur anywhere between TG and TM0. Higher TC, larger crystals, smaller TC, or lower TC, smaller crystals. And it turns out that if we're interested in the crystallization rate, how fast the crystals form, and there's a theoretical reason for this that you'll learn later, the crystallization rate is fastest halfway between TM0 and TG. It's just a really interesting, useful rule of thumb. So if you have a polymer and you want to get the maximum crystallinity into that polymer as you're processing it, you want to hold it halfway between TG and TM0 for a time to let it fully crystallize. And of course, no crystallization or melting can occur below TG, and we just talked about quenching as well. So these are some bullet points that you want to remember for TM and TC, including that there's delta H of fusion can be calculated from TM or TC peaks. That's important because you could figure out the percent crystallinity from those peaks. Yes.
If you were to quench from TM to TG, would the polymer itself be more expanded because it's still melted? It'd still be in the same conformation as melted.
Well, you want to quench it from TM to below TG to stop it. If you just quench it to TG, you know, you're in sort of a strange region. But if we look at,
well, I guess that my question was more TM to below TG. Like if you were to just quench it from there to below TG, would it be like in the same expansion as it when it was melted?
Yes, yeah, so it would have excess free volume, and that's what this says. So if you cool a polymer fast, say from the melt, so if this is not above TM0, you can have some crystals there, and if you cool it fast below TG, you have this excess free volume, which is basically those chains are frozen in their conformations like they were in the melt with a little bit more free volume. Is that good?
Yes.
Yeah. Yes.
So usually when we quench, the material becomes tougher,
It It depends. It really depends on the details of how the quenching is done and things like that. Now, some excess free volume can be good for toughness, but it can also make the polymer really brittle as well because the chains aren't as consolidated. So it depends. Quenching, it turns out, is expensive, so we don't use it a lot to process polymers that fast cooling, although some polymers are cooled pretty fast, but they crystallize really fast. And so it just depends. Yeah.
I was just thinking because aren't crystals supposed to be brittle?
So, well, this is a good question. So the question was, aren't crystals supposed to be brittle? And mineral crystals we think of as brittle, right? So calcium carbonate, ice, we can fracture those crystals, right? What's the difference between small molecule crystals and polymer crystals? Does anyone have an idea? Polymer crystals are made out of what? Well, there's covalent bonding in the crystal, but also the polymer, go ahead. Long chains. The long chains can weave together crystals. And this isn't really in this class for what polymer crystals look like, but it turns out that polymer crystals are really unique because you can have one chain form a crystal here, and then another chain comes in, makes crystal here, and maybe this chain is part of a crystal up here, etc. There's another chain, comes in here, makes a polymer crystal. And so these chains knit together the polymer crystals. And the crystals themselves are organic molecules with covalent bonds in the crystal. So polymer crystals are really tough. Or let's say are strong. And we know polymers are already tough. And we call these chain folded lamellae. These are tie chains. Let's say there's some amorphous here. And they hold together crystals. And these parts, of course, are amorphous. So that's really cool. There's some amorphous part in a semicrystalline polymer that gives it toughness. There are these tie chains that hold everything together, and the crystals themselves are really strong. They decrease the permeability. They allow us to use polyethylene at room temperature for packaging and stuff like that. And so there's all sorts of really interesting things when we have semicrystalline polymers. And that's why they're most useful. Polyethylene and polypropylene are the most used polymers on the face of the earth, and they're semicrystalline, so they have great properties. You'll learn all of that in the future. It's very cool, trust me. So polymer crystals are not brittle like we think of inorganic crystals. All right, that is all I want to talk about in terms of thermal properties. That's all I want to talk about in terms of thermal properties. And so as you start to review and think about your homework, I'll have a list of things to remember. And that sort of builds our understanding of characterization, and how we know what we have for the properties of these polymers. So we've covered SEC, N group analysis, thermal transitions, we're not going to cover some of these, but another really important aspect of polymer characterization is mechanical properties. Of course, a lot of materials are used for their mechanical properties in the first place. Why do we build buildings out of steel and concrete? Why do we build iPhone cases out of polymers? And so we really want ways to start to characterize the mechanical properties of those polymers, and that's what we're going to talk about next. All right, so you could look at these questions. All right, let's switch over to mechanical properties right here. It turns out that the mechanical properties of rubbery polymers or polymer liquids are really important as well. Because if we're going to use a rubbery polymer, like a rubber band, what state of polymer is in that rubber band, do you think? It's an elastomer, it's flexible. And so do you think that polymer at room temperature is above its TG or below its TG? Or does that rubbery material have a high or low TG? Your rubbery materials have low TGs, right? So at room temperature, you're above the TG of that rubbery material, and it's acting kind of like a liquid. It turns out that rubber bands are cross-linked, so it can't flow, but even the properties of rubbery polymers or polymer melts or polymer liquids are important because they're really important for elastomers and other things. All right, so the Challenger explosion happened when I was in second or third grade. I watched it on TV because they used to stop school for space shuttle launches, and you'd all watch it on the TV in school. It was really awesome, except Challenger was a huge disaster, but we used to watch shuttle launches all the time in grade school because it was brand new. It was a marvel. It turns out, has anyone here heard of Richard Feynman? Yeah, what do you know Richard Feynman for? Quantum, right? Feynman diagrams. He was in the golden age of quantum mechanics with all the people that invented the field. And he was a really famous mechanician and physicist at Caltech, but he was also a really good science communicator, it turns out. But he was on the commission that investigated the Challenger explosion. Why did it happen? And it turns out, you can Google this if you want, it turns out that the Challenger explosion in part was due to a leaky O-ring seal because it was too cold the morning that they launched the space shuttle. So because they're using O-rings to seal these solid rocket boosters, if it's too cold, all of a sudden you're dropping below the glass transition temperature of your elastomer, and your elastomer goes from a nice rubbery elastomer that can seal and do its job to some sort of glassy, hard polymer that's not good at sealing anymore. Because when you launch a rocket, lots of things expand and contract, and so you need really good rubbery seals in that case. And so Feynman, it's this famous proceeding. He takes a piece of the elastomer that they use when they're testifying before Congress, and he dunks it in his ice water, and he says, look, this isn't an O-ring anymore when it's cold. When I dunk it in the ice water, it's a brittle piece of polymer and it's not going to seal, and that's why this happened. There are other reasons why, but basically the Challenger explosion was due to the glass transition temperature of the seals that they used in the solid rocket booster. That's very interesting. Okay, so because polymers are these long chains of molecules, and we've talked about entanglements and other things that they do, remember the word that we used like in the first couple of lectures to describe a special type of property of polymers? Like when they move, what do we call that? Polymers are viscoelastic. And it's easy to see where viscoelastic comes from. They have properties of viscous materials, and viscous materials are liquids. And they have properties of elastic materials, and elastic materials are solids. And so polymers have the properties of both liquids and solids, depending on the situation, depending on the temperature, depending on the time scale, all sorts of stuff. And so we need some basic understanding of how fluids or how liquids behave, what the viscosity is, and what the behavior of elastic solids are in terms of these properties, and that's handled by Hooke's law. And so we'll talk about viscosity, Newton's law, we'll talk about elasticity, Hooke's law, and we'll put those together in order to come up with some really unique things that polymers do in terms of creep, stress relaxation, and other relaxation processes. Now, when I say relaxation, relaxation of what? What's moving in a polymer? So I take a polymer, I stretch it, and then it relaxes. What's that?
The chains.
That's right. The chains are moving around, or the chains are doing the relaxing. And relaxing is just a sophisticated word for the chains are moving around. And where do polymer chains really want to be? Or how do polymer chains really want to move towards? What's their equilibrium conformation of a polymer chain? If I stretch out a polymer chain and I let it go, what does it really want to do? Coil back up, right? It wants to assume its equilibrium end-to-end distance, or whatever end-to-end distance it is depending on the molecular weight. So as soon as I stretch out a polymer and I let it do its thing, it's going to want to contract. And so if I stretch out a bunch of polymer chains in this, let's say this is a solid piece of plastic, if I stretch this out and I let it go, those chains are going to want to relax. And so this thing is going to shrink. That's a very unusual property. Usually when I stretch something and I let it go, it stays there, right? Not polymers, because those chains are coiling up. And so think about this idea of chain relaxation and how the polymer chain movement back to some sort of equilibrium coil is going to influence the properties that we're going to talk about next. Any questions or comments so far? All right, so think like polymer chains to understand what's going on here, because we're going to talk about some time-dependent mechanical properties. So some of you have taken mechanical properties class already. They may have covered viscoelasticity a little bit in there, but viscoelasticity is all about time-dependent mechanical properties. And it's time dependent because chains need time to move. Great. Elastic solids, viscous liquids, put those together with long chains, you get time dependent properties, and that allows us to figure out what's going on with polymers. All right. So you want to keep your stress and strain straight. You just have to memorize this. There's no good way to figure this out. And so it's always stress, strain. Strain is a length measurement or dimensional measurement, percent elongation, some other thing like that. So it can be unitless, and it's usually unitless, or it can be in percent. What's the units of stress? Pressure, force per area. So the unit is going to be pressure. So if you're feeling lots of stress, you feel under pressure, right? That's how I remember it, or force per unit area, which is a normalized load. So you pull on something with a defined force, and depending on the cross-sectional area of that thing, that's the stress or the pressure you're putting on it. And we always plot it in this configuration. So no matter if you're doing a stress controlled experiment where you tell the computer, put 100 newtons of force on this thing, or you're doing a strain controlled experiment where you say, pull the sample 30%, it's always plotted like this, even though you can do the experiments different ways. All right, so we have our definition for stress, force area equals pressure. And then strain is defined as the change in length over the original length. So you could see that diagram right here. Change in length delta L over L0. That's the definition of strain. And you could express that as percent or whatever you want. But in this nomenclature, strain is unitless. Okay, that's all we want to cover. But this is going to be important because we're going to look at stress strain curves. I'm not going to tell you the units, or I'll have you draw a stress strain curve, or you're going to have to tell me what's a soft material versus what's a hard material. And so when you have a hard material or a high modulus material, is the stress going to be high or low for a given strain? High. It's hard. I got to pull on it, right? And if it's a soft material, the stress can be low and I can strain it. So you want to build up your intuition for how that looks. Okay. Hooke's law is what we use to figure out what springs do, right? What's the spring constant? That's maybe where you've encountered Hooke's law before. And springs are what? Are they viscous or elastic? Elastic. And in the ideal case, they're perfectly elastic, which means they have a linear stress strain curve that starts at 0. And as long as you're in the linear regime, you can strain it and it'll go right back. Let go of that stress or strain, it'll go right back. So same thing with a hard material, right? So this is high modulus. So it's got high stress at low strain. This is a low modulus. It's got low stress at high strain. So this, the open spring here might be something more like a soft elastomer or something that's really elastic. This might be something more glassy and hard, right? This solid block. So formally, the linear part of the stress strain curve is called the Young's modulus. And we usually say at low extension to make sure we're in the linear regime. This coefficient, E, is the Young's modulus. And so this is the equation of a line. Remember, we have Y, we have X, and geez, that's not a very good Y. And the slope of that line is the Young's modulus. That is the definition of Young's modulus. The last thing that you want to remember is here we have stress strain curve. We have our Young's modulus. And this is cool because this area under the curve is the toughness. So we say a material is tough. There's a scientific definition for toughness that you integrate the area under the stress strain curve and you get toughness from that. So think about some of these definitions. If you've never done mechanical properties before, this will take some learning, and then we'll continue to build this. Yes, one question.
So what I think of it is Young's modulus is derivative, and then
Well, it's just yeah, so it's the slope because it's a straight line, so you could say it's a derivative, and then toughness is of course the integral, yeah. All right, see you on Monday.